Now that we've been introduced to vector fields, let's start to think about trajectories. Trajectories are going to be a representation of the solution as it lives inside the state space. Okay, I'm going to start with some one-dimensional examples, and here I've drawn out 3 one-dimensional examples that go from the simplest thing possible to a little bit more complicated to a little bit more complicated still. These are the state equations in this column. And here in this column, I'll be drawing the state spaces with the vector fields for each example overlaid in blue. And then here, I'm going to give you an idea of what the corresponding time series looks like for each of these examples. So notice here in this time series column, the horizontal axis is time because the independent variable is time. In the state space column, the horizontal axis is the state because state spaces only showcase the dependent variables, and in this case there's just one, there's just the x variable. Okay, so let's start with our simplest example, which is going to be x prime is equal to 1. That means x prime is equal to the constant number 1 no matter what the state is. What kind of feedback is that? No feedback at all. That's right, because if my rate of change is always equal to 1, no matter where I am, then my rate of change is not looking to see what the state is in order to determine what its value should be. So the rate of change equation is not a function of x, it's just a constant 1, and so it doesn't have any feedback at all in it. And what does that vector field look like? Well, because it's not looking to x to determine its value, it's simple. I'm just going to graph a 1, 1, 1, 1. I'm going to graph the same exact vector. Those might not look exactly the same, but I meant for those blue vectors to all have the same exact length no matter where I am. Each of those vectors is exactly the value 1. No matter what state I'm in, the rate of change is always equal to 1. Does that sound familiar? What kind of time dynamics do you think I have if I told you that my rate of change is always equal to a constant? That's right, that's a linear function. As you recall from pre-calculus, linear functions are those who have a constant rate of change. The slope, m, is the rate of change. And so what I'm going to draw for the time dynamics here is I'm going to draw a linear function that starts somewhere and it just marches up by 1, 1, 1, 1. For every time unit that goes by, my x state variable is going to go up by 1, and I end up getting a line for my function of time. Okay? But that equation isn't really any fun because it doesn't have any feedback, and feedback's the whole name of the game, right? So let's make it a little more complicated and say that instead of x prime just being equal to 1, let's see it's equal to 1 times x. So this is a simple example of the more general form of the equation x prime is equal to rx, where the parameter r, that's usually the constant of proportionality in front here, I've just left that as a 1 for sake of simplicity. I'm going to draw the vector field in the state space here for x prime is equal to x, and let's try to carefully look at the difference between this case, where the vector is always the same exact length for every value of x, versus this case over here, where depending on where I start for the x value, I'm going to have to look at this function to determine what I should draw for the vector. The easiest thing to do, I guess, would be to start with x equals 0. And if I plug in the state x equals 0 into the state equation, I get x prime is equal to 0. Again, what does that look like? A 0 vector has no magnitude, no direction. It's not really going anywhere. It's really stable. It's really just staying right there. Oh, sorry, I meant to draw that in blue. So if the vector is equal to 0, then you'll just draw it as a dot. And later you'll see that that's going to denote an equilibrium point as for our time dynamics later. I'll just make that nice and neat for you there. So the vector field's value at the point x equals 0 is simply equal to 0. Now, because x prime is equal to x, as I march forward in greater and greater positive values of x, I'm going to end up getting vectors for my vector field that are larger and larger and larger still. So maybe I exaggerated a little too much, but what I'm trying to do is emphasize the difference between the behavior for our constant rate of change and a rate of change that depends linearly on x. You see, in both cases, a simpler form for the dynamics of the vector field, the simplest form in both cases would just be to draw an arrow pointing to the right. But I'm trying to overlay it at different points of the state so you can really see that there is a difference. They're both pointing to the right, but this one is accelerating at an accelerating pace, really. This one results in exponential behavior as opposed to linear behavior with the constant rate of change. So the corresponding time dynamics in this case would be if we started in roughly the same place that we started up here, instead of growing linearly, I'm going to be faster and faster and faster and faster, and that growth is going to be exponential. Okay, so the previous example was an example of linear growth, and this leads to an example of exponential growth. Exponential. Had to put that on 2 lines because it's getting so big. Yeah. Okay, so on to our next example in which I've layered another bit of complexity on top. As we know, exponential growth can't go on forever when we have some sort of limiting resources such as space or a limited amount of food. And so really this model is better refined by adding this other part to it here that speaks to the amount of resources that are left to get. Again, this is a subset of the more general logistic form where I would have Rx times 1 minus x over k. And so like this one above, for this one, I've set all the parameter values to 1. But really, there's a growth parameter r out in front here, and there's a divided by the carrying capacity parameter x divided by k here. I've also let the k equal 1. Okay, so again, let's go back to layering the vector field onto the state space. Just like the previous example, if x is equal to 0, and we plug that into this equation here, we're going to get 0. And so we do have just a dot there. I can't help but call it a fixed point because that's what it is, as you'll see. A place where the rate of change is equal to 0 right there. And as we've seen in the logistic model previously, there's one other special place where x prime is going to result in a value of 0. And that's for the state that exactly corresponds to the carrying capacity k. So here, since I've let k equal 1, when x is equal to 1, as you see if you plug it in here, then just like where x equals 0, you get this dot here where the x prime is equal to 0. The vector field is equal to 0. The rate of change is 0. It's not changing at all. In between these 2 points here, as we saw in the last video, the output from this function is going to be a positive number. And so we're going to get vectors that are small at first, getting a little bigger, eventually get kind of big at the peak right between the 2 roots here, right between 0 and 1, when as x is equal to 1/2, that's when this function will be maximized. That's where the peak of that down-facing parabola was. And then once we pass that, as we approach the carrying capacity, the rate of change gets smaller and smaller again. Rate of change is equal to 0 right there at the carrying capacity. And if we go past that, and we actually have a larger population than the carrying capacity can hold, that's when the output from the rate of change gets negative. And the larger, the further away from the carrying capacity we are, the more past it we are, the higher that negative rate of change will be. So the more negative the output will be, resulting in a larger and larger vector for the vector field that's pointing to the left. What does the time series look like for that? By now, hopefully you've seen the time series for the logistic model a couple times. And that's one where if you start with a little bit, it starts to look exponential like we have above here. But once we start to approach the carrying capacity, the rate of change says, now hold it. Hold it. You're getting close to how much we can really hold. So you need to calm down a little bit and start to mellow out. And by the time you're at the carrying capacity, you're just at a stable, that should be a flat line there. You're just at a stable value where your graph is pretty much horizontal. Okay, and that is going to be located at the value of the carrying capacity, which I've set to 1 for this example. All right? If you actually started with a population value that's over here and it's larger than the carry capacity, what you would have in a logistic model is you would have kind of an exponential decay where we're approaching this equilibrium value right here at 1. Okay, and so those are kind of 2 instances. Sorry, it's a little sloppy there. Those are 2 instances of time series of solutions to the logistic model. But time series showcasing the solutions in time is not exactly what they mean by trajectories. What trajectories are their depictions of where a solution is going to go from a particular starting place or initial condition inside the state space. So a trajectory inside the state space for the logistic equation, maybe if I started right here, a trajectory would look like this. I'm going to approach 1. I'm never going to quite get there, but that's for later. It kind of goes towards 1, right? A trajectory in this sense is exactly this black arrow that I've drawn here, where no matter where you start, you're just going to keep going and going and going and going, and you're just going to keep going along the line. Okay, so those are all one-dimensional examples, and hopefully you're starting to appreciate the information that you can get when you see a trajectory in the state space versus a trajectory in a time series. What we're going to do next is we're going to kick it up into 2 dimensions here, and we're going to do our shark versus tuna example. And I know that this is the moment you've all been waiting for, so I'm finally happy and proud to bring you Okay, that's right. I have 2 of them. That's just for fun. So we have our predator, baby shark, and hopefully he'll shut off in a minute. And then we have our prey, which is the tuna. This is about as close as I could get. And the predator is chasing the prey around and around the state space here. We kind of worked on the vector field. This is about how far we got in the last video. But now we're going to see the trajectory as the tuna travels this way and the shark chases it around, and it's going to go around and around in the state space. And then we're going to attempt to draw what that corresponding trajectory looks like in terms of the time series. All right, so now here we go with the real exciting stuff. First, let's take a look at the trajectory. Now, I know that in the last video we kind of showed evaluating this vector field. By the way, in the last video I used x prime and y prime, but hopefully you can appreciate that this is the same equations that I had in the last video, and these are the same equations that describe a general dynamics of a predator versus a prey situation. In general, when we have a predator, we assume that the predator grows exponentially on its own, and it is taken out of the system, eliminated due to interactions with the prey. Oh wait, I totally said that wrong. Okay, I'm sorry. What I meant was the first one is the prey, okay? And so the prey is on the horizontal axis here. I'm sorry if I misspoke before. But tuna is the prey, right? So the prey is what's going to grow exponentially on its own. Think about like bunnies or kales or tuna in the sea. It's got something else to feed on, and there's plenty of that something else. So it's going to grow exponentially on its own. But then it's going to die off as it interacts with the predator. Here, the predator is the shark. Okay? Conversely, the predator, if left on its own in the presence of no prey to eat, is going to die out exponentially. That's why we have a minus here. Usually in the general model, we would have 1, 2, 3, 4 parameters, one sitting in front of each of these terms, but I've set them all to 1 just for simplicity. So here, the minus here denotes the fact that in the complete absence of prey, the predator is going to die out exponentially because it has no food, and what's giving it life is its ability to eat the prey. So that's why this is a positive term here. It's positive for the predator, it's negative for the prey. I put some resources for you to be able to graph this vector field using some websites online. And that's really what you want to do so that you can see a real nice visual of the entire vector field inside of the state space. I'm not going to be able to draw that by hand right now. That would be probably hundreds of arrows in order to look really nice. But go ahead and check out that online resource link that I have in the description of this video and practice out by plugging these equations in. When you use those resources, keep in mind that the first variable always needs to be denoted as x, and the second variable always needs to be denoted as y. And so you might want to transform that back into the equations I had in the last video so that you can copy them into the resource. Click graph vector field. You might also have to put a little multiplication times symbol here and here in order for it to work. But if you do get to work, then the whole vector field opens up to you. And I'll get rid of these two vectors that we had practiced on and replace them with what's called a trajectory. So a trajectory in the state space is something that starts somewhere. It's always got to have a starting point, and here we're going to call that the initial condition. Let's say that we have an initial condition with a lot of tuna and not so many sharks in the sea, right? And then what happens with the initial condition is it starts to follow the vectors around, and it just kind of lets the vectors tell it where to go. And in this case, if you're looking at the vector field using those resources online, you'll see that it starts to point this way, and it goes up like this, and it comes back around, and it forms this closed loop that's rotating in that counterclockwise direction. I could have also drawn this trajectory for some other paths, like I could have also drawn other trajectories for other initial conditions. Like if I started here in the state space, I might end up in a closed loop that looks like this. If I started over here in the state space, I might end up in a closed loop that looks more like this. Now these aren't really drawn perfectly by hand by me right now, but again, if you click on those links in the description and plug in these equations using x and y for the first and second variables respectively, you'll get to click on your own initial conditions and you'll see them start to get drawn on top of the vector field. And if you look really closely, you'll see that those curves, those trajectories, are following the vector field around. Everywhere we are, the vectors that represent the rates of change are always tangent to the actual trajectory that's getting traced out. Kind of gives you an inkling of why we might be calling that a tangent space. We'll talk more about that later though. Okay, so that's the idea of trajectories in the state space, but really the biggest idea here is how do we go from state space, where trajectories are kind of tracing themselves out, and time is an implicit parameter. Time is just seen by the action of my finger here rotating counterclockwise. It's not explicitly graphed. How do we go from that and pull out an actual time series? This is pretty difficult, but it is doable, and I recommend using the online link there where you're going to see that there's a tab down below where you can also see the time series. That's really convenient. So here, remember that trajectories in two different state spaces can kind of look similar. Like for these two examples, they both just look like an arrow pointing to the right. But it doesn't mean that their time dynamics is going to be the same. Because as we know, linear and exponential growth in time are two totally different things. So we got to watch out for that. And that's not explicitly graphed on here. Time is just this implicit parameter that's kind of parameterizing the dynamics as it moves through the state space. All right, let me try to give you an idea using red for sharks and blue for tuna of how you're going to transfer a trajectory in the state space into a time series graph. Okay? I'm just going to pick one of these trajectories. Maybe I'll pick this first one that I started with here, and maybe I'll say that, okay, you know what? This actually gets pretty tricky, and I have a little trick that is going to help you do this. Here's a little trick that you can do if you need to go from trajectory graph to time series graph. One thing that I like to do sometimes is I like to draw the diagonal line where y is equal to x. Watch this. Okay, so on the state space, I've given myself help by drawing in the line, what's called the diagonal or identity line, where y is exactly equal to x. And that's because if I choose a place on a trajectory that intersects the diagonal line, y equals x, then I know that that corresponds to a point in time in the time series where the two state variables are equal to each other. Does that make sense? In this case, our state variables are actually t and s, and so instead of calling this diagonal line y is equal to x, I might call this diagonal line s is equal to t instead. But the idea is the same. You can easily draw a line that represents the diagonal, and what it does is it gives you kind of a place to start. Because you see, that's where I hesitated, was like, maybe I want to take this outer trajectory and turn it into a time series, but where do I start? Well, a nice place to start would be right here, where on this trajectory is intersecting with a diagonal line. And what that means for my time series, if I denote that as time is equal to 0, is it means that sharks and tuna are starting out at the same amount. And so sharks and tuna and sharks are both starting out at this initial condition that I'm marking right here with this dot here. Okay, I'll start with the tuna because that's the prey, and I will try to draw what my finger is tracing out as my finger traces this trajectory in the state space. I'll try to draw in the time series, okay? Now, I knew that this blue line and the red line should start low, and that's because T and S are both relatively small at this point. When I take my blue marker and I try to draw the time dynamics just for the tuna, what I'm going to do is I'm just going to think about the horizontal component of the XY point as I travel through time. So I'm just going to think about what the horizontal, or T, or X first variable is doing, and I'll try to draw it as that progresses through time. Okay? So time is moving in the forward direction as I move counterclockwise. The way I knew that was by looking at the vector fields, and the vectors are pointing this way. So my tuna starts small, and just thinking about the horizontal component, ignoring all aspects of the vertical component, it seems that my tuna populations get bigger and bigger and bigger and bigger and bigger until about right here. Okay, and so I'm going to draw a tuna population that's getting bigger and bigger and bigger and bigger until about right here. To help us out, what I'm going to do is I'm going to kind of mark some time points on this graph. It might help if I get rid of these other trajectories so I can just focus on this one trajectory. And I'll put the diagonal line in there. Really, remember, I just drew this dotted line for my own good, my own sanity, as a place to give myself a place to start, and later a place to check in, where S and T are going to intersect each other in time later. So I'm going to call this my initial point T equals 0 right here. And then maybe I'll call T equals 1, this bottoming it out. You see how it kind of goes down and then it goes back up again? I'll call this T is equal to 1. And then maybe this corner point right here, I'll call this T is equal to 2. Now let me show you where those time points go on the time series graph as I've kind of decided where to label them moving along the trajectory. T equals 0, that's our starting point. Remember that this is a graph in time, and so this is the starting point in time. As my tuna population increases, T is equal to 1, I denoted right there for some reason, kind of a middle time between my starting point and the point at which my tuna population has finally peaked. And so I'll just mark this as time is equal to 1. And the place where my tuna population finally peaked, I will call that, oops, it's really messy when I actually erase something. I'll call that time is equal to 2, right there, where the blue graph is at its peak. Time is equal to 2 is right there. You see, this is about as good as it gets for the tuna. This is as far over to the right as this trajectory is going to get. And so what that means is that's the highest the tuna is going to peak in time. After that time, the tuna is going to start getting smaller and smaller and smaller. And the reason I know that is because the trajectory horizontal component is moving to the left, all the way until I get to here. Okay, so my tuna is going to go down, 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 and then it's going to bottom out again. And let me just throw some more time points on the graph here, and then find their corresponding place over there. Let's call where it hits the diagonal again, t equals 3. And let's call this point where t pretty much gets to its lowest state, t is equal to 4. Now, rightly, this point I marked as t is equal to 4 is a little bit before before the tuna really dips down to its lowest, because it goes to the left just a little bit more. And so here I'll say that this is equal to t is equal to 3. And right before that final dip, I'm going to mark t is equal to 4. Okay? So once I've hit t is equal to 4 and then I dip down and I bottom out, what happens is I return to the original position I was in my initial condition again. And so that's why I know that the bottom of my dip here is going to be very close to my starting point right there. That seems to be about one cycle going around on this periodic trajectory, one cycle of the tuna's time dynamics. Now let's do that again for the sharks. And since I've already built up these calibration points of time, I'll be able to think about those as I draw the red curve that represents the sharks. When I start to think about the sharks, I'm just going to be looking at the y or vertical component of the xy point in the trajectory, and I'm going to ignore the horizontal or x component. Okay, so at time is equal to 1, you can see that the y component is small, but it's not exactly at its dip yet. It has a little bit lower to go. And then right here, kind of conveniently so, I picked this timestamp t is equal to 1 to represent when the y component is at its lowest. So what I'm going to draw over here is sharks that are low but not quite at their bottom yet. And by t is equal to 1, that's when the sharks are at their lowest population value. Then the shark population starts to perk up, and it gets higher and higher and higher. At the point t equals 3, that's when the shark population intersects the tuna population. So I'm going to keep that in mind. At the point t is equal to 3, the red line that I'm going to draw is going to intersect the blue line that I've already drawn. That's why I drew the diagonal on there, to kind of give myself that little place, that location, to know when these are going to meet up again. Okay? So between 1, 2, and 3, it looks like just the vertical component is going up, up, up. And it's even going to go up even more past that. But for now, I'll kind of denote that like this, where I've tried to make a point that these two things are going to intersect right at t is equal to 3. Geez, I think I missed the mark a little bit. Let me try that again. Let's see, t is equal to 3. I want to make sure I get this really exact because it's just nicer that way. Okay, so you see at the time point t is equal to 3, the red line and the blue line intersect in time. How do I know that? Because I've decided to make that timestamp as the place where the trajectory intersected the statement that sharks are equal to tuna. The diagonal line is really helpful to know when two curves are going to intersect in the time space. Okay, what happens to the sharks as we go from t is equal to 3 to t is equal to 4? As I travel over here, well, we can see that the horizontal component is getting smaller and smaller. It's going to the left. That's why the blue line, the tuna, is going down. But the vertical component is still going up, and it hits its peak right around here, and then a little bit past its peak is where I put the timestamp t is equal to 4. So with my red pen to denote the shark dynamics in time, Between times 3 and 4, I know that it's going to go up and it's going to peak, and then time is equal to 4 is just past the peak of the red line. So I'm going to draw it like this. It goes up and it peaks, and then it's t is equal to 4, just a teensy bit past that peak. All right, and I know that this is a cyclic thing that's going on, so that as I return from t is equal to 4 back to t is equal to 0, really it might be on to another timestamp t is equal to 5, but we're on a cycle here, so we're going around and around. So what happens there is that it looks like the x component between 4 and 0 again. Oh, maybe I drew that blue line a little wrong, actually. It looks like as we go on between t is equal to 4 and maybe, let me call this next step t is equal to 5. It's just on a cycle. That's why it happens to intersect with 0. The blue component is staying relatively stable, relatively the same. And so what I had drawn for the blue line there, as I showed it going up again, but that's not really the true story, so sorry for that mistake. What I really meant for that was that the blue line is kind of topped off. It's kind of just hanging out, just staying stable, because you see the horizontal component is really staying the same. And then it'll start to go up again as we go from t equals 5 to 6 to 7 or something like that. Okay, glad I corrected that. And now back to the sharks, where I'm just going to be looking for the vertical component. And the vertical component takes a nice sharp dip down, right? Well, that's probably because there's not enough tuna around. That was a good correction that I made just now, because it's really highlighting the reason for why the sharks are about to take a deep dip down like that. The shark population is going down because the tuna population is steady at a low value, and although the sharks experienced a boon because we had so many tuna before, now that the tuna has gone down, because as the sharks ate them, their population went down, tuna population is low, shark population is going to respond, and that's going to be low too. Now it's time to start your adventure all over again with our first video, 1.1 on feedback, where you can see pretty much the same story played out with the snails and the kales. That was a predator-prey model too, and so you're going to see that this kind of oscillatory behavior where a prey goes high and then the predator kind of responds to that by increasing, and then that lowers the prey, and then that lowers the predator because it responds to the prey. That kind of dynamics that we saw with the snails and kales and the sharks and the tuna can also be seen with the rabbits and the foxes and the chickens and the eagles, and so many other predator-prey systems have this kind of hair and lynx oscillatory behavior.